I mentioned last time we're going to continue our discussion with adders and arithmetic functions in general. Now, just as a refresher, the half adder. Oops. The half adder is just a exclusive OR gate and an AND gate, providing the sum and I'm sorry, getting everything mixed up. Sum and carry of adding two bits together. And then the full adder is two of these together. So you have A, B, and carry in. The exclusive OR gate here. Exclusive OR gate here. That's your sum. And then your two AND gates ORed together for your carry out. Okay, so you have your two half adders in the full adder. So this is and full adder. Now, how you link these together to do addition with a larger binary number, you would have your, let's say 4 bits. Let's do another one down here. You have your half adder here, and the out, the in, the out, the in, the out, the in. This would be A0, B0, A1, B1, A2, B2, and A3, B3. And you would have your carry out and sum and these are full adders. And this would be your sum 0-bit, sum 1-bit, sum 2-bit, sum 3-bit, and sum 4-bit, 4th bit. So that's how you would link together adders, full adder, a half adder at the beginning and full adders afterwards, to make what's called a ripple adder. So this is called a ripple adder. The reasons why it's called a ripple adder is this bit here is not valid until the carries from the first half adder and and then the full adders, they ripple down. So when you first put the 4 bits of each argument into the adder, the ripple adder, it's not a valid output. It takes a little bit of time for the result to ripple down all the way to the end. So this is what's called a ripple adder. There are circuits known as look-ahead adders, which can calculate the sum all at once, but the circuitry for that is a lot more complicated, and quite frankly, I don't think I could fit it on the board and not have it look like a pile of spaghetti as far as the lines crisscrossing each other go. But the ripple adder will function and works just fine. Now, when you get into subtraction, this works for addition. When you get into subtraction, what is subtraction? But adding a negative number, right? It's a number that you add. Subtracting a number is adding the negative of that number to the first number. So you can use this adder as a subtractor as well by making b a negative number. So how would you do that? Well, if you recall from number systems at the beginning of the semester, you invert the bits and add 1, right? That's 2's complement. And then you can add the negative number to the positive, or the first argument, and get a subtraction operation. To do that, you would selectively, should have drawn this a little bit lower on this board, selectively invert B. With an XOR gate. So this line here will be, when this line here is high, it will invert the B bits. Right? You remember that from the A, B, out. So if you assert the A pin, if the A pin is 0, the output is going to match B. So that's your addition. For subtraction, you want to invert B, so you make A high, and it makes B inverted. The output is the inverse of B. So it will selectively invert the B bit in the input of the adder. But that's only part of it. That's what's called 1's complement. You have to add 1 to make it 2's complement. So you make this a full adder, and you have the carry in with the subtract line. So if the subtract line is high, you will selectively invert B and add 1 to the addition and sum, thereby making it a ripple adder and subtractor. So the same circuitry can be used for both addition and subtraction, with the addition of the XOR gates on the second argument of the subtraction. So that is one way of doing the addition and subtraction of, in this case, a 4-bit number. But yeah, like say you have 0, 1, 1, 1 that you're going to be subtracting from, and you're going to subtract minus 0, 1, 0, 1. Okay. You would invert the bits. And add and then add 1. Let me. And add 1, and then you would get 0, carry the 1, 1, carry the 1, 0, carry the 1, and 0, carry the 1. And then this would be, the upper bit would be discarded because of the vagaries of 2's complement addition, and you get 0, 0, 1, 0 as your result. Now, if you look at it, this is 7. This is 4 and 1 is 5. So 4 minus 5 equals, this is 2. So the math works out perfectly. So yeah, that is how addition and subtraction can be done in circuitry. Really snappy, instead of in doing it in software. But now multiplication is a little bit more complicated because, the method of multiplication is can be done in a similar fashion to how we do long multiplication. So let's just take a two-bit number. Let's say 3 times. Let's do a 3-bit number. 3. Let's say 5 times 3. That's 4 and 1 is 5, and 5 times 3. How you would do that on paper, a multi-digit number on paper, sometimes called long multiplication. Multiply in the first row, 1, 0, 1. Then you shift 1, repeat the process, 1, 0, 1. And then here is 0, 0, 0, because 0 times any number is going to be 0. And then you add it together, and you get 15. Okay, that's called the shift and add method. You shift your products, your partial products. These are called partial products. You shift them one position for each position on the lower factor, and then you add them together. How this can be implemented in circuitry is using a combination of AND gates, which, if you recall from Boolean algebra, behaves like multiplication, and adders. So you have your first row of your partial product. You have, let's see here, A0 or A2, A1, A0, and then you have B0 and B1 and B2. This will be A and B, bit 0, 1, and 2. Your first partial product is going to be B0. I'm sorry, I did this wrong. Labeled this wrong here. B0 times all the A bits. And that's done with AND gates. All right? That gives a partial product. Then you have A0 again. You shift. So you have A0, B1, A0 B or A1 B1 and A2 B1, and you multiply those together. And just as a refresher, on the AND gate is is multiplication. See, 0 times 0, 0, 0 times 1, 0, 1 times 0 is 0, and 1 times 1 is 1. So it is multiplication for one bit. Okay? And then you have running out of room, grew too big. Uh, let's just say let's say B is a 2-bit number for right now. That's going to be your product bit 1, product bit 0. These are going to go into an adder. Add these two together in a half adder, and that's going to be your product 1. These go into a full adder, and your C out here goes into C in here, and that's P2, and uh, it goes into a half adder, another half adder, carry out is P4 and P3. It's C out. You can see how it is shifted and added together. You shift the partial products 1 bit for each bit that you are multiplying the first number by. So in this case, we have two bits that are being multiplied by the first number. So you do the first bit of the second number multiplied by all the bits of the first of the first number. Then the second bit of the second number times all the bits of the first number, shifted because the B1 bit is shifted 1 in this method, and add the results together. So you just shift and add. So this would be a shift and add hardware multiplier. So Does everybody see why the multiplication and addition works in this type of hardware multiplier? Is it making sense? You multiply to make partial products using AND gates, and then add them all together. Just like you would multiplying 432 by 48 by hand. You know, the same shift and add method, only with ones and zeros. So processors often have hardware multipliers built into the circuitry of the CPU or the ALU, and can execute multiplication fairly quickly. I believe in computer architecture, you will study how to do the shift and add method in software for those processors that don't have hardware multipliers. Although I honestly don't know of any processors offhand that don't have hardware multipliers that are still in production. Older processors might still have the microassembly software to do the shift and add method. But it takes quite a bit longer to do that because each instruction takes time to execute and takes multiple instructions. It's basically it basically is a shift and add, but it's in a loop that runs, and when you do loops, that just takes up CPU time, that sort of thing. When you have a hardware multiplier like this, you send it to the ALU, spits out a response fairly snappy, and you get your result. So, but yeah, that's how a shift and add hardware multiplier works. I'm going to kind of shift gears. I think we're running a little bit behind. Where are you guys at in the lab? What, have you done K-maps? You've done K-maps. Have you gotten to SR latches yet? And flip-flops? No, not yet? Okay, well, we're going to start on the SR flip-flops right now. Or SR latches right now. If everybody's got this down, or at least down in their notes. Right. All right. Now, a computer wouldn't do very much good if it didn't remember things. So, the most basic element, basic form of memory that you can create with digital logic is a pair of NOR gates what's called cross-coupled. Okay, and this is an SR or SR latch, or RS latch. It's called either one, depending on who you're talking to, or the manufacturer. But this is what's called sequential logic, where the outputs feed back into the inputs of the circuit. So what you have here is when you look at the state table, if S and R are 0, both 0, Q and Q prime remain unchanged. They remember their previous state. I'll trace that through in just a minute. If the S input is high and the R input is low, Q will follow S. And Q prime is the opposite. And if you go back to 0 and 0 again, it will remember that 1 and 0 from the S being set. If you then add, do the R, it resets the Q and inverted Q prime. It resets the Q to 0. And again, go back to 0, 0, 0, and it will remember that state. Now, where you run into problems with the SR latch is 1, 1. This is undefined. You don't really know what's going on with it. And I'll trace that through right now. So the S and R stand for set and reset. So if S is 1 and R is 0, you have 0 here because 1 NORed with anything is going to be 0. This 0 is going to be over here, come down to the input of this NOR gate. 0 NORed with 0 is going to be 1. This 1 feeds back into this NOR gate. 1 NORed with 1 is going to be 0, so that's stable. Okay? Now, if you switch them, go back to 0 here, go back to 0 here, 0 and 1 from this, 1 NORed with 0 is going to be 0. 0 is going to feed back into this. 0 and NORed with 0 is going to be 1. It remains stable in the same state that it was before. Okay? If you assert the R, make that a 1, the Q is it going to be 0, NORed with 1 is going to be 0. That 0 is going to feed into here. 0 NORed with 0 on the set is going to be 1. 1 goes back into here. 1 NORed with 1 is going to be 0, so it is stable. Okay, Q, the output, the primary output, is going to be reset to 0 when you have the reset set to 1. Now, change the R back to 0, and 0 NORed with 1 from the Q prime is going to be 0. 0 NORed with 0 is going to be 1 for the Q prime. So it is a stable state. It remains unchanged from the previous state. And when in this case, it can act as 1 bit worth of memory. Set it with the S bit, reset it with the R bit. Now where it gets kind of weird or unstable is when you have S and R both being 1. 1 NORed with anything is going to be 0, right? 0 comes down here. 1 NORed with 0 is going to be 0. Supposed to flip flop back and forth. Yeah. Yeah. Well, 1 1 NORed with 0 0 is going to be 0. 0 comes down here. 1 NORed with 0 is 0 here. So Q and Q prime being the same is not allowed. It's undefined. When you, unless you take them off exactly at the same time, it can jump to either set or reset depending on the timing of the signals. You can't time everything to exactly perfect. So when you take off the if you take off the R first, it'll see the set as the last stable state. And if you take the S off first, it'll see the reset as the last stable state. Signals don't travel 100% accurately synchronized. So when you come off this state, you don't know necessarily what state you're going to be in the when you drop the signals. So what the next logical step to this is what's called a clocked SR latch. Oh yeah, or I need a new eraser. Where you have AND gates on the inputs, Basically, if the clock is low, 0 ANDed with anything is going to be 0. So it's going to be the 0, 0 state. When the clock is high, the SNR will pass through to the NOR gates. So the uh, 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 and if the clock is 0, everything is unchanged. And this here is unchanged. And then this is 1, 0, 0, 1, disallowed. So that's the state table with the clock. You have the SNR can be anything. It doesn't matter if the clock is low, then the outputs here are going to remain unchanged. But you still have that disallowed condition down there at the bottom. So what you can do is make sure that the SNR are not the same value. You can easily do that by adding an inverter and tying them to the same input. Call that D. Now this becomes a clocked D latch. Now the clocked D latch yeah, that's right. D clock, clock low, D doesn't matter, Q, Q prime are unchanged. Clock is high, 0, 1, 0, 1, 1, 0. That's the state table for the D latch. So as long as this is also called a transparent latch. You should remember that term as well. If the clock is high, the input is followed on the Q output transparently. So sometimes it is called a transparent latch or a transparent D latch. But the D will follow the Q, Q will follow the D when the clock is high. When the clock is low, the outputs are latched, and it doesn't matter what D is, Q and Q prime will remain unchanged. Getting to be more like memory, huh? But now the oh, I should have put this up here before. Let's hear the SR latch is typically drawn like this as a block diagram or block symbol. Clocked SR latch is going to be more like that. And then the D latch is going to be a symbol such as that, similar to that. You might see a bubble on the Q prime because it's inverted from the Q. So you might see that on a schematic as well. How are we doing on time? We're doing okay. Now, also the clock also can be called the enable bit, latch enable. So here it might be represented by a EN instead of a CLK. And put it right there too. So there's a lot of variety in what symbols are used, and depending on who's drawing the schematics, that sort of thing, you might see different labeling and all that sort of stuff that means the same thing as what is quote unquote standard. I think we'll call it a day with that. Next time we will get into flip-flops, which are edge triggered, where they take a snippet of time and go by the state of the inputs at a particular instant in time, and as opposed to being transparent while the clock is high. Anyway, have a good day. See you on Thursday.